Good morning once again. I will now take you through another counter, which will be the T synchronous counter. Once more, I'm going to go through each of the steps with you, and then I'm going to go through each step in more detail. Again, the steps are the development of the state diagram, then the development of the present state next state transition table, then we simplify the expressions, and then finally create the circuit. So once again, here we're going to be a little bit more bold. We're going to create a 3-bit counter, synchronous counter, which means we'll be needing 3 T flip-flops. So first we create the state diagram. As can be seen, the 3 bits, and then we have them connected to each other. So once again, we have 0 0 0, which will then be linked to 0 0 1, which will be linked to 0 1 0, then 0 1 1, then 1 0 0, 1 0 1, 1 1 0, 1 1 1, and then back to 0 0 0. So we have our state diagram. We can now move onto the present state next state transition table. So again, we have our present states AN, BN, and CN, and our next states AN plus 1, BN plus 1, CN plus 1. And once again, we have all of the present states linked with the corresponding next states. So once again, I'm just going to go over the first topic with you. The first row, I apologize, with you. And yes, again, we're going to need the excitation tables to reference. So for TA, we know the present state will be 0, and we know the next state will be 0. So here we look at the excitation table, 0 and 0. T, the input needs to be 0, so we place the 0 here. And the exact same thing will happen for TB, because again we have 0 and 0 here. So once more, 0 0, input needs to be 0, which we place here. Finally, for TC, we have CN, the present state, being 0, and CN plus 1, the next state, being 1. So we look into the excitation table, present state 0, next state 1. The input needs to be 1, and once again we place that in here. So I'm going to again take a short pause so that you can now fill in the rest of the table. Alright, great. Your table should look similar to mine. If not, once again, correct it please, because we need this to be correct for us to simplify our expressions properly. So the next thing we do is once again simplify the expressions. We use the inputs which we found here to do this. So I'm going to go through each of them with you really quickly. So the first being for TA, we have 0 0 0, which is 0, placed here. 0 0 1, 0, placed here. 0 1 0, 0, placed here. And 0 1 1, which is 1, placed here. Next, 1 0 0, which is 0, placed here. 1 0 1, which is 0, placed here. 1 1 0, again 0, placed here. And 1 1 1, which is 1, placed here. Again, now we're going to go to TB. So 0 0 0 is 0, placed here. 0 0 1 1, placed here. 0 1 0 is 0, placed here. 0 1 1 is 1, placed here. Then we have 1 0 0 0, placed here. 1 0 1 1, placed here. Oops. 1 1 0 0, placed here, and finally 1 1 1, which is 1, placed here. As can be seen, all the inputs are 1, so we can simply just place all ones in the final K map here. So as we now group we see that the ones here, this is the one group, which will be BN and CN, which are the outputs of the B and the C flip-flops. We go here for TB, and we see this is the group, which shows that CN, the output for the C flip-flop, the third one, will be connected to the input at B. And finally, we see for TC, since the entire thing is grouped, it will be equal to 1. Alright, so now we are going to take a look at how we implement the circuit in Logisim. Alright, now we will look at the implementation of the circuit in Logisim. Again, this is a setup that you should have in your tutorial. Now we're going to just walk you through how you connect the rest of the wires using the logic of the simplified expressions. So we'll start with the third flip-flop, C. So as can be seen here, TC is equal to 1, which is a high input. So we connect the 1 to C. That's it. We then go to here, the B flip-flop. We see that TB, the input, is equal to CN, which is the output of the third flip-flop, this one. So we then connect the input, the output, sorry. Oh my goodness. Sorry. We then connect the output to this flip-flop. And once again, that is it. And finally, we go and we connect, we figure out what the input is for this flip-flop here. So we see TA is equal to BN and CN, which means it is equal to the outputs of both the B flip-flop and the C flip-flop when it's high. You need to know that when it's 1. So that is why we have an AND gate here, because if you remember, when both inputs of an AND is 1, that is the only time when the output will be 1. Any other case, it will be 0. So we place the AND to make sure that the input, that only when both the outputs of B and C are 1, then it will input 1 to the A flip-flop. So we connect this, and that is it. That is the entire setup right here. I'll just take you back to the state diagram so you can see the counter in action. So once again, we're going to simulate, enable, and we'll see. It starts at, as you can see, 000, then it goes to 001, 010, 011, sorry, 100, 101, 110, 111, and then finally back to 000. So as you can see, this is our T synchronous counter.